Hi, everyone. We're so thrilled to have you here with us today to listen to Dr. Danny Lange, who's the Vice President of Artificial Intelligence and Machine Learning at Unity Technologies. The title of his presentation is On the Road to Artificial Intelligence. Thank you, Danny.
Thank you very much. Very excited to be here. I'm going to talk about the journey towards artificial general intelligence. I'm not going to talk much about the destination itself. My focus is really on all the exciting things we're going to go through in the process, in the journey towards AGI. So very happy to be back at this conference. I've been here, several times before. So let's get going. Just a very quick introduction of Unity. We are a real-time 3D platform. We are known, for gaming and a bunch of other verticals. But the key point is that we are currently powering more than half of the world's games. And some numbers are really big. Over 4 million downloads a month, 2.3 billion monthly active players. And we're 3,500 employees. We're headquartered in San Francisco. But, we're a game engine. So games have really been used to drive AI research for a long time, yeah? So games have played a crucial role in advancing AI from a very early point with Claude Shannon and his chess algorithm from back in the late 40s, 49, 50. There's a nice paper about that work. Checkers is another example of a board game that was used to drive AI. When I was at IBM, Deep Blue defeated Garry Kasparov in chess, Watson in Jeopardy, and more recently, DeepMind's work in the Go board game, initially with AlphaGo and then AlphaZero. All of these board games have helped advancing the field of AI. If you move into the video game space, we've seen a bunch of research being driven by Atari games, Doom, Quake, Minecraft, StarCraft, Dota, and Unity's own Obstacle Tower Challenge. All of these video games have basically been used to challenge AI and test and evolve algorithms. Yeah. So let's try to get into this question here of what it is that links video games with AI. Yeah. And to do that, we need to take a step back and think a bit about intelligence. This is the dictionary definition of intelligence, the ability to acquire and apply knowledge and skills, but that's still fairly abstract. So what I like to do is I like to sort of think about the only real intelligence that I truly know, which is the intelligence in biological systems. So I'm going to take more of an empirical approach here and basically look at the role of intelligence in nature. And I think it's driven by five principles. Number one, we need to eat, we need to consume substance. And while we do that, and this is not just humans, it's animals, it's all living beings. We have to, while we consume energy, we need to avoid getting eaten ourselves and become energy for someone else. We need to become more abundant. We, as individuals, we have a limited lifespan, so we need to keep the species alive. And we need to be aware of physics in all of this because we can fall, hurt ourselves. We can fall over a cliff from a tree and kill ourselves. So physics matters. And finally, there's the role of agency, the ability to build a nest or a home to improve survivability. Those five principles are really driving survival in nature. And that nature created this to enable the intelligence needed to survive. Yeah. So it created all this infrastructure from chemical mechanisms all the way to sensors such as touch, sight, hearing, taste, and smell, and many, many other sensors in nature. Yeah. All of this infrastructure is really to create intelligence, to survive, to increase survivability. Yeah. And if you just relate that to a real-time 3D engine. Yeah. So you have in such an engine, in a game engine, you have a spatial environment, you have 3 dimensions, you have a physics engine with gravity, inertia, collision, and you have you have that in a controlled, self-sufficient ecosystem, yeah. And in many ways, it closely replicates the real world. You actually have the fourth dimension, which is time. You have sequence in a game engine, yeah. So taking a starting point out of the game engine, yeah, let's see what we can do around learning scenarios driven by a gaming engine. So in nature, reinforcement learning is basically the fundamental function, yeah. And I'm going to be a little loose on the definitions here. There's sort of learning, but there's evolution too. There's learning built into the evolution. I'm sort of going to be a little loose here and combine those two. And the way it works in nature is that we basically observe and we take some action. And this again is both, you know, as learning process takes place as we grow up, but it's also the way that nature works. Yeah, there's some action taken, which can be random or more or decided on in other ways, and then we reap the rewards and the penalties from that. Yeah, so we basically move from an exploration to an exploitation in the world. Yeah, so at Unity, my team asked themselves, you know, can we have a good example of that? And some of you have probably seen me showing this example before, but this is essentially the chicken crossing the road. Yeah, can a computer system basically be trained to have the chicken safely cross the road with 4 actions, left, right, forward, backward, and 2 reward signals. One that is negative, -1 for being hit, and +1 for picking up a gift package. Yeah. And if you look at the video, it starts from scratch. The chicken has absolutely no idea. This is the initial learning phase. It moves, you know, randomly around, more backwards than forwards. But in a moment, it will pick up a gift package up on the right there, and then it will get killed. Yeah. So 2 bits of information within a few seconds. Yeah. Having done this for some time, it gets actually pretty good at it. It does pick up most packages, and it avoids a couple of cars, and then it gets killed. Yeah. So it's not perfect yet. Yeah. But you already see here that by simply trial and error over and over and over with a generic learning algorithm, the chicken is able to make some real smart decisions. But watch, after 6 hours of training, it becomes superhuman. Yeah. The chicken basically will avoid these cars coming in, and these cars are coming in randomly. So it's not like it tried the same scenario over and over and over. This is completely random, has never seen these particular combinations of vehicles and packages before, yeah, and will deal safely with them all. Yeah. So this is a good example of reinforcement learning. Let's try to put it into different contexts. I'm going to go through a number of scenarios here. Control learning, yeah. A quadruped learning to move. It has actually 8 joints, 8 little motors that need to move in some pattern or act in some pattern to have this quadruped moving from left to right. Yeah, it can be learned just the same way as the chicken learned it. Yeah, you see this example here. It's having a humanoid learning to stand. Yeah, anyone who had a small child at home, they recognize this around the 12 months age. There's a lot of joints that needs to be controlled here. Yeah, you take it a step up, and these guys here, they are completely reinforcement learned in all their movements. They're not super great in the animation, but it's not that bad if you think about it. It's just learned from scratch. Yeah. In other examples here, where you have an industrial example where you basically have robots that learn to touch an object. Yeah, so they need to also move a lot of joints. Yeah, so you see humanoids, quadrupeds, universal robots here. It's all control learning. Yeah, curriculum learning is another example that I want to bring up. It's basically where we found that going through grades like in school, like, don't let the reinforcement learning system start out with the most difficult task first. Instead, start easy and make it harder as it graduates on each little task. In this case here, the agent needs to scale a wall, and it needs to use tools to help it scale the wall. Yeah, and we found that if you raise the wall gradually and you only raise it when the agent has become really good at scaling it, it works much better. Yeah. So in this case here, you see it's actually when the wall is low, it will just jump over. When it gets a little higher, it will use the cube as a stepping stone. Yeah. This task is better learned stepwise rather than just throwing the agent into the deep water. Something we see, of course, with humans and animals as well. We are very good at curriculum learning. Yeah. Memory learning is another example where we add the capability to the neural net to have a recursive element of memory. In this case here, we basically have the agent picking the exit of the color of the big cube in the middle. Yeah, if the cube is orange, take the orange exit. If it's red, take the red exit. Yeah, and through reinforcement learning, we actually only say yes or no, plus or minus, as it being trained. Yeah, we never tell it it's the color. It actually learns that it's the color that matters. Yeah, and it remembers that color all the way to the exit. Yeah, so it's an example of having a what we call LSTM, long short-term memory, in your combined with your reinforcement learning here. I already showed you the quadruped. Here we have hierarchical learning. So we have two machine learning models. One model is basically directing the quadruped, go left, go right, go straight, towards the target. And a second model, the one I showed earlier, is basically having the quadruped move. Yeah. Multi-agent learning is also an interesting field here. In this case, we have two agents with a common goal of keeping the ball in the air. Yeah, so they play together some sort of tennis here to avoid the ball hitting the ground. Here we have an adversarial example. We have two agents playing soccer against each other. And what you keep a careful eye on these agents. When one agent is moving up in an offensive position, the other agent is moving back in a defensive position. And then they switch roles dynamically. It's very interesting to see how they learn this kind of relatively strategic behavior of always making sure that when one is offensive, the other is defensive. Yeah? I also find this example here of 2-on-1. So two blue players are playing on the purple agent. The purple agent is actually defending the goal, yeah? But look, at most of the time, the purple agent is very offensive. And it's really an example where it learns, in reinforcement learning from scratch, it learns that being offensive is the best defense, literally. Just keep the ball far away from your goal against these two opponents. So I want to talk a bit about traits in learning. This is a very funny video. Someone sent me this video and said, I bet that your deep neural net cannot do this, yeah, cheating like this, yeah. Well, look at this next video. This is an example of the agent trying to jump over the wall. And look what happened in one of these training sessions. It figured out it's just much faster to go around the wall, yeah. This is something we found that these traits we like to call them cheats, but that's really just because we want to, put a word on it. It's just basically an optimization challenge, yeah. So if it's easier to get around the wall, that's what it will do. But I want to talk a bit about these traits in a somewhat larger context. So it's extrinsic, intrinsic rewards. We have seen a lot of examples of extrinsic rewards. It's what we call getting rich. It's collecting points, yeah. But intrinsic rewards are really things like curiosity, impatience, happiness, and love. Nature gave us those traits for a reason. They increase survivability, yeah. So let's see if we can use this. We have some examples of very sparse reward space in reinforcement learning. Yeah, it's where you have very improbable scenarios. So we have one scenario where the agent enters a room, needs to find a button in one of these rooms, push the button, a pyramid will appear. It needs to tumble the pyramid to collect the intrinsic reward, the gold bar. Yeah, and we found that random exploration just will not work for that. We need to have what we call intrinsic rewards. We need to have a method to the exploration here. And what we did is that we basically put math on what curiosity means. Yeah, we basically pick curiosity as an intrinsic reward that's perhaps useful. Yeah, and with curiosity, what's point here is actually the minus log in the rewards function. Yeah, what you basically train the agent to do is to identify any given situation, to identify the target in its environments that it knows the least about, that it's the worst at predicting. Yeah, normally in machine learning, we try to do the opposite. We try to minimize the error. Here, we're maximizing the error. Yeah. So look at this example here. The agent is moving around in this building of rooms. It's random exploration, and it's not very productive. It's not getting anywhere. Yeah. So clearly, just extrinsic rewards are not really going to get a result here. Yeah. Let's move to an example where we have curiosity only. Yeah. And look how it moves from room to room, because it's curious. It always wants to look into a new room. And then in a room, it sees stuff. Yeah. Stuff that it doesn't know what does. Yeah. So in this case, it figures out that it can tumble the thing. Yeah. So curiosity drives a much more determined exploration. Yeah. And then put curiosity together with the extrinsic rewards, and you get a very determined agent that is really searching for that button, hit the button, then searching for the pyramid with the gold bar, hit that, tumble that pyramid, and pick up the gold bar. Yeah, and here we go. Yeah, so an example of the value of intrinsic rewards, such as curiosity. But of course, look what happens here. If I put a TV set in front of the agent, we have what we call the TV trap, because there's an unlimited unknown things to look at here. So the agent will get stuck and watch TV all day instead, which means that that you have to have other intrinsic rewards, such as impatience, such that the agent doesn't get stuck here, but at one point get bored and moves on to something else. Yeah. Let me show you a cute little example here. This is where we put it all together, and we basically train a mechanical virtual puppy robot here. All the animation, all the behavior here is reinforcement learned from scratch. Yeah, so there's no animation design here. There's no artist in here. I throw the stick, and the puppy will pick the stick. Yeah. So it's really, in all of this, it's really synthetic data that is unlocking all the research here. Yeah. When I play a game, it runs at 30 to 60 frames per second. But when I run a simulation, training an AI, I have essentially, I can run as fast as the machinery will allow me. Yeah. So I can, in essence, have unlimited frames per second. Yeah. And if you think about it, 1 year of your life at movie rate of 30 frames per second is 1 billion frames. Yeah. I can run faster than the 30 frames per second with a game engine. Yeah. I can put it on powerful hardware. I can put it on a massive amount of hardware, so I can do large scale deployment. And I can also interact with the environment when I work with synthetic data. Yeah. So everything I've shown you here is how to use the game engine to really advance AI and generate enormous amount of data. Yeah. I also hope that you saw from my presentation that biology has a lot of interesting stuff in store for us. Yeah, so it's things like attention, episodic memory, working memory. I showed an example of that. Continuous learning, imagination, which is Monte Carlo tree search and simulation. Intrinsic values, I talked about that. Hierarchical learning, I gave you an example of that. Biology is basically rich. I'm not copying biology, I'm getting inspired from it. Yeah. And then if we move on and we start to think about how human culture has evolved at its own time scale, 200,000-300,000 years ago, Homo sapiens appear. There was migration that failed, but about 45 to 70,000 years ago, some global migration out of Africa happened, and we went all the way across the globe to Australia. And that happened at the same time that we see things like this. We see things like abstract pieces of art appear around 30, 40,000 years ago. And we talk about that as the cognitive revolution. Yeah. Now, what you have to remember, there's no Moore's law for the human brain. Yeah. So all this happened This cognitive revolution happened without any updates or upgrades to the hardware. Yeah. So what was it that happened that basically led to this dramatic evolution to where we are today without any hardware changes in our brain? Well, it's things like emergence, language, collaboration, and anticipation. Yeah, it's these concepts. And what I wanted to sort of seed with you with my talk today is that all these little examples I give, they're all little, bits of building blocks for emergence, language, collaboration, anticipation. Yeah. So I hope that you can sort of see a road ahead where we scale that up, where we combine that in increasingly complex patterns and basically work our way towards a greater level of intelligence similar to what happened to humans. That was all I had in store for you. I hope this was exciting to you. It's definitely exciting to me. I invite you to visit unity.com because you can actually download all these examples I showed you. All that code is available under ML Agents, called ML Agents. It's on GitHub. It's all open source. Yeah. Feel free to link with me on LinkedIn and Twitter. And let me end the show here and take some questions.
Thank you so much, Danny. We have a couple of questions. Please feel free to continue to add them as we go through them. The first question we have is, did you try to improve game graphics using AI at Unity?
Yeah, we actually have some numerous efforts underway to use generative nets to create better textures and to improve the graphics. It's a very, 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 very rich field. It's very exciting. Also things like generating terrain and going even further, actually generating it's not as much the graphics, but also the behavior of, say, characters in the game. Yeah.
Got it. Okay. Another question comes to us from Anonymous. Are there similar use cases in conversations?
I didn't quite get similar use cases in conversations.
Mm-hmm. In conversations, yep.
Yeah. So so everything I showed you here is kind of really behavioral. Yeah, it's graphical, it's behavioral, it's physics, it's 3D. When it comes to natural language into conversations, there's some very, very interesting opportunities here, because what you can do is you can start tying language to positioning in a 3D environment. You can actually train a system to understand, put the blue cube on top of the red cube. Yeah, move the cube left, move it right. So you can basically have a infinite system of interaction using language, and it's an excellent way of sort of moving natural language processing, NLP, from sort of being limited to what's written on Wikipedia or whatever, to sort of a very open-ended world where language and physical interaction play together.
Got it. We have one more question. Isn't it equivalent to consider a trait like curiosity or impatience as its own extrinsic reward?
Yeah, this is a lot about words. Yeah, I think that what the way I define it is that extrinsic rewards are external to the agent, is to the environment. I compare that, it's like a car in front of your house or a bank account. Yeah, intrinsic is purely within your head. Yeah, it's happiness, it's love, it's impatience. It's not. It's inside you. So it's really intrinsic to the agent. Yeah. And in that I prefer to see it that way, because then it's really hard to, like curiosity is not like there's a specific reward at the end of the day. It's not like you maximize your curiosity by gathering points. Yeah, it's just at every single step there's a specific rewards function allocated to curiosity. Yeah, but you don't try to win by that.
Mm-hmm. And I think we have time for one last question. So apologies to Mujtaba. Perhaps you can reach out to Danny directly. From Anonymous, we have, are you working with any computer-aided engineering companies?
Yes, we are, because what you see here is we're giving examples on behavior, but imagine that I'm trying to design a building with windows, and I want to maximize the sunshine coming in through the window through the year, every day through the year. There's a lot of simulation going on here, and you need reinforcement learning to learn to sort of optimize the building layout and the windows as respect to the seasons and the sun. This is an example of some of the stuff that we're working with partners and customers on.
Great. Thank you so much, Danny. That was very, very informative. I learned a lot. I hadn't heard you speak before. And thank you for everyone that joined us. Look forward to seeing you on the next meeting.
Thank you much, everybody.